Okay. So last time we talked about, well, we introduced sort of some stuff about carboxylic acids. Let's see, we talked about hydrogen bonding and a little bit of nomenclature. And then maybe most importantly, we talked about why carboxylic acids are acidic. And that's because when we deprotonate a carboxylic acid with a base or something like that, we get an anion that has a resonance structure like that. And then so if you combine them like the one on the right, we get a resonance stabilized, delocalized ion, the carboxylate ion. And so that's fairly stable. So carboxylic acids are acidic. And then I also mentioned that carboxylic acids are sort of intermediate in between most organic compounds like alcohols or, well, water is not an organic compound, but that would be down there as well. Intermediate between those and inorganic acids like hydrogen chloride, sulfuric acid, etc. Okay, so today we need to talk about the synthesis of carboxylic acids. As a reminder, no lab for Bluffton people next week, but we'll have lecture as normal. So synthesis of carboxylic acids, we've got 4 different ways that we can do this. The first is ozonolysis of alkynes. So in the last chapter, we talked about making ketones and aldehydes using ozonolysis reactions. But if we have an alkyne, where we have a triple bond instead of a double bond, we can do a similar type of ozonolysis reaction. We treat it with ozone. And in the case of the alkenes, we split the double bond down the middle, and one of them became one ketone and the other became the other ketone. And so we're really going to do the same thing here. So we're going to split the alkyne down the middle. And instead of replacing it with an aldehyde or a ketone, we're going to replace it with a carboxylic acid. So we do that on both sides with R and R prime. And so we get 2 carboxylic acids. Now, this is especially useful if R and R prime are the same thing. So if it's, a methyl group in both cases, then we'll get 2 molecules of acetic acid or whatever carboxylic acid you want to make. So that's ozonolysis. That one's a little bit less obvious because you see a carbon-carbon triple bond, and I don't know about you, but the first thing I think of is not, oh, let's make a carboxylic acid out of that. It's, I don't know about obscure, if that's the right word, but that's one method. The next one is a bit more clear-cut or obvious, and that is the oxidation of primary alcohols. Again, going back to the aldehyde and ketone stuff, we said that if we took a secondary alcohol and oxidized it with some specific oxidizing agents, we could make a ketone, something like that. And this is a very similar reaction. So we'll take some primary alcohol where we've got 2 hydrogens on the carbon attached to the alcohol. That's important. And then we use our choice of oxidizing agents, chromic acid or potassium permanganate. That is going to oxidize the central carbon there all the way up to the carboxylic acid. So why is it important that it be a primary alcohol? Well, in the carboxylic acid product at the end, you've only got one R group. There's no hydrogens on the central carbon. And so in order for that to happen, we've got to have a starting alcohol that only has one R group attached to the central carbon. And the way to do that is to have a primary alcohol, where you have 2 hydrogens along with the OH group. There were a couple other reagents we talked about during the aldehyde and ketone section that you can also use for oxidations, like PCC, DMP, that sort of stuff. But in this case, those, especially PCC, are not adequate. And if you were to treat this starting material here with PCC, you would only get an aldehyde. So you need a stronger oxidizing agent, like the chromic acid or potassium permanganate, to get that second oxygen onto the molecule. The third way is the hydrolysis of nitriles. And so to do that, we need a nitrile. Another similarity here to actually both of the examples we've talked about. I just mentioned that we've got to have only one R group on that primary alcohol in the second method. And then also, if you go back and look at the ozonolysis, those carbons that are part of the alkyne only have one R group and 3 bonds to something else. So if we go back and look at the nitrile, RCN, well, we have 1 bond to an R group and then 3 bonds to nitrogen. And so during our hydrolysis reaction, which is going to use H3O plus, that's just aqueous acid like hydrochloric acid or sulfuric acid or something like that. We're going to keep 3 bonds between carbon and something else and the bond to the R group, but those 3 bonds instead are going to be to oxygen. So in all cases here, we are preserving the oxidation state of the central carbon. And so basically that means same number of bonds let's see here. So this counts for this one and also for hydrolysis of nitriles. However, the oxidation state of the carbon does change in the oxidation reaction, hence the name. Same number of bonds to R group and two heteroatoms. Like nitrogen or oxygen. So these are three perfectly valid methods that you'll probably need to use at some point. But the last one is totally the coolest, and I'm kind of a nerd, so bear with me here. But the last method is the carboxylation of Grignard reagents. So we know that a Grignard reagent is our MgBr, which we make from the alkyl halide, we add magnesium, et cetera, but for this part, we'll just start with the alkyl magnesium bromide. Usually what we would do is first add a ketone or an aldehyde or something, right? So like one, and then we hydrolyze it with water, et cetera. But, okay, let's pretend, so here's kind of what a ketone might look like, right? We've got a carbon-oxygen double bond. That's kind of the important bit. That's what does the reacting. And then we've got two R groups of some kind. But what if instead of having two R groups, we just put another carbonyl on the other side of the molecule, the same carbon? What's that? Carbon dioxide. Yeah. So we can actually use carbon dioxide as an electrophile in the Grignard reaction, just like it's a ketone or an aldehyde, because in some ways it kind of is. It's still got that CO double bond. So we'll use CO2, and I'm going to draw this out sort of stepwise here. So from that, we get this molecule. And I think you can see here that there's our CO2 molecule. Starting to look like a carboxylic acid as well. And so now what we do is we add some water or some acid. Really need some acid in this case. And that's going to protonate our carboxylate and give us a carboxylic acid. And again, there's our CO2 molecule that's been incorporated. Really, we're just taking the alkyl bromide, the RBr at the beginning, and inserting a molecule of CO2 and putting a hydrogen on it. The way you actually do this in the lab, and unfortunately we're not going to have time to do this experiment, but you make your Grignard reagent, which you have to do under like air and water-free conditions because it's pretty sensitive. And then you get a beaker of dry ice, solid CO2, and you just dump your reaction mixture onto the dry ice. And it does that reaction, and then you throw in some acid, and you get your carboxylic acid. I don't know. I just think that's kind of fun to do. One note about this reaction is that we add one carbon to the molecule. Now, okay, maybe that's kind of obvious because yes, we're adding a molecule of CO2, so that has a carbon in it, so it's going to be added. But sometimes it trips people up, specifically when you look at an actual example. So let's use this alkyl bromide, which has 3 carbons. So I'm going to call it a C3 molecule. And we make our Grignard reagent. This is also 1, 2, 3, a C3 molecule. And then we do actual Grignard reaction where we add carbon dioxide. There's our carboxylic acid product that we get. But if you count the carbons, 1, 2, 3, 4. So there's 4 carbons on that molecule. So you just got to make sure if you want to use this method to synthesize a carboxylic acid, the R group that you start with has to be, well, the R group can be the same number of carbons. In fact, it has to be because the R group stays the same. But if you're just looking at the actual reagents that you're going to use, you need to remember that, right, this carbon here that's attached to the bromine is not the carboxylic acid carbon. It's that one right there. So that might seem kind of obvious, but when you're rushing to do a synthesis problem or something like that, you do this reaction, just have to keep in mind that you're always adding 1 carbon atom. When we do nitrile chemistry, probably next time, we're also going to see that reaction or those types of reactions can be used to increase the carbon chain by 1 as well. Okay, questions on the synthesis of carboxylic acids? Now, these aren't the only ways, but all the other ones we're going to talk about relating to other functional groups like hydrolysis of another functional group into a carboxylic acid or something like that. Okay. So that's synthesis. Now, there's a lot of different reactions that we can do with carboxylic acids. Most of them, again, we'll have or we'll talk about in the other sections. But an important reaction specifically is the reduction of carboxylic acids, because these don't result in another carboxylic acid derivative. They result in a oxygen-based functional group of lower oxidation state. Anyway, so we can reduce 2 alcohols. And this is done by treating our carboxylic acid with lithium aluminum hydride, LiAlH4, and then acid. This gives you a primary alcohol. So that's the reverse process that we talked about from the chromic acid or the potassium permanganate. So you do it the way I've written it here, but one caveat is that this reaction always goes to, sorry, not the carboxylic acid, the alcohol. It cannot stop at the aldehyde. So if you want to do that, say you'd like the aldehyde instead, we have a method to get from the aldehyde to the alcohol. That you can just use sodium borohydride, that's last chapter. But to get just to the aldehyde, which is an intermediate oxidation state, so between the acid and the alcohol, in oxidation state, the reagents for that are kind of funny and weird looking. We need TMS chloride, trimethylsilyl chloride, which is a silicon atom with 3 methyl groups and a hydrogen. And then the other reagent we need is called Dibol H. Bit interesting, but it's an acronym. It means diisobutyl aluminum hydride. Oop. Diisobutyl aluminum hydride. And so it's got aluminum hydride, and then it's got 2 isobutyl groups. There we go. 2 isobutyl groups on it. Okay, so sort of exotic looking reagents. And the reason for that is, well, if we use sort of our less exotic looking reagent, lithium aluminum hydride, that's a really strong reducing agent. And so it's going to reduce it all the way down to the alcohol. But if we only want sort of a mild reduction just to the aldehyde that will stop and not go any further until we treat it with something else, then we need a more selective variety of reagents, in this case, trimethylsilyl chloride and Dibol. I did these both at the same time, didn't I? There we go. Okay, let's do an example. Yes, yes. So I'm going to show you that the drawing is kind of ugly. So let's look at an example. Let's do this molecule, which is sort of similar to benzoic acid, but not exactly. And let's say that we want to make that alcohol. But also, we want to make the aldehyde. So do the carboxylic acid all the way down to the alcohol, we could do this whole process at the bottom where we use TMS chloride and dibol and then use sodium borohydride to reduce the aldehyde to the alcohol. Or we could just be sort of lazy and use lithium aluminum hydride followed by acid workup. Now, if we tried to do that in the second example, well, we're going to get the same alcohol as our product. And we don't want the alcohol, we want the aldehyde. So for this reaction, we need TMS chloride. You can just write that. You don't need to draw out the whole structure. Just want you to have seen it. And dibol H.
So on the exam, would you give us like how we started with just the lines and the two like beginning and ending parts?
Maybe. So this will make more sense once I give you the homework, but generally I will either give you the starting materials and reagents and say, okay, predict the products, or I'll give you, like I did here, the beginning and the end and say, okay, tell me what you need to make this transformation. Or I'll give you the final product and some reagents and say, okay, what material must I have started with? No, those aren't that bad.
Yeah, like so you'll give us two parts at least.
Yeah, I'm gonna give you two parts and you figure out the third part. Generally. Yeah. We'll do some more practice. Don't worry. Okay. So that's all I want to mention about carboxylic acids themselves. And we've got a couple more derivatives that I want to review. So esters. Esters are really important in a lot of industries. A lot of flavorings and like perfumes and stuff are esters. And the other nice thing is that they aren't super reactive molecules. And so a lot of times there's some really strong synthetic methods we can use to make them. But then the reactions that esters do aren't, I guess they're not quite as interesting, and they aren't quite as common because a lot of times your target material is an ester, so you're just trying to get to that point. But we'll see that in some examples. So how do we make esters? The first method we can do is an SN2 reaction, actually. So we know for an SN2 reaction, we need a nucleophile and an electrophile. Well, most reactions, we need a nucleophile and an electrophile. So let's start by making a nucleophile. And we'll do that starting with a carboxylic acid, unsurprisingly. If we deprotonate the carboxylic acid with a base like sodium hydroxide, we get carboxylate ion. And now this is a good nucleophile. So we can give it an electrophile with, whoa, I need to eat lunch. An electrophile to react with. Like an alkyl halide. So we can draw sort of a ghetto mechanism here where R prime is just the carbon of whatever we're talking about. And that's an SN2 type mechanism. And so what do we have as a result of this reaction? Well, X is our leaving group. And so we've got X that has come off. We've also, a sodium atom has been floating around. And so we're going to get a sodium salt of X, so sodium chloride, sodium bromide. something like that. But as the organic product, we're going to have, so there's the part that comes from the nucleophile, the carboxylate, and then, okay, we've made a bond between the oxygen that had the negative charge and R prime. So there we go. There's our ester. So that's making esters by SN2. The second one, we have just done in lab, Fischer esterification. So if you kind of recall what we did in lab is we took a carboxylic acid. In our case, it was salicylic acid. We added an alcohol. What was our alcohol? Methanol. It's an equilibrium process, and as our catalyst, we used sulfuric acid, but the important part of the sulfuric acid here is the H+. And from that, we got an ester that smelled like wintergreen, oil of wintergreen, and as a side product, some water. So this reaction is an equilibrium reaction. It's reversible. So we need to use Le Chatelier's principle to control which direction the equilibrium goes. Sorry if I'm giving you flashbacks to the lab quiz, but what's the answers to the lab quiz? Okay, what was the question? It was how do we encourage more formation of the product, right? So the product is our ester. That's what we're trying to make. So how do we upset the equilibrium? Well, we can add more of the carboxylic acid. We could add more of the alcohol. We can't really, I mean, we could, but it's not going to be useful to change the amount of catalyst. Is a common wrong answer. And the reason is the catalyst is only there to speed up the reaction. It doesn't affect the position of the equilibrium to the left or right, even though it kind of feels like it sometimes, but it doesn't. So our ester is our product. We're trying to make more of that. And so the other thing we can do is decrease the amount of the other side product, which is water. So those are the answers. Increase the amount of alcohol or methanol, that was one of them, and decrease the amount of water. So as I said, the process is a reverse, we have the reverse reaction too. And so that reverse process is ester hydrolysis. Okay, so let's look at some examples of that. What example shall we use? Oh, maybe the lab example. So there's salicylic acid. Methanol was our alcohol. And so right on our salicylic acid, we've got two functional groups that look like they might react in some way. And so one of the things that will come with some more practice is determining, ooh, we have an alcohol and an alcohol reacting. No, not really. So that means that our OH group here is not really going to be reactive in this case. Instead, we need the carboxylic acid, and that's going to be what does the reaction here, because Fischer esterification is between an acid and an alcohol. Okay, so that means that that OH is going to stay the same. And then on what used to be our carboxylic acid is now the R group from the alcohol, methyl group. And so we just put our methyl group right there. And so that is methyl salicylate. And of course, as a side product, we have water. We can do the opposite reaction. So I could draw the example where methyl salicylate reacts with water to give you salicylic acid and methanol, but I'll use a slightly different set of reagents. So this is methyl benzoate, which actually has a pretty similar smell to methyl salicylate. In fact, it's the same molecule just without the OH group. But the methyl benzoate, I don't know, I think it smells like medicine. Kind of like the wintergreen minty smell, but more like cough syrup. Hence why I picked salicylic acid. Anyway, so if we take methyl benzoate and we react it with water, generally not much is going to happen. But if we add an acid catalyst, now we can have some sort of reaction. And so we're going to split apart the ester functional group. And so in the same way that we start the salicylic acid reaction with an acid and an alcohol, this hydrolysis reaction is going to give us an acid and an alcohol. So that acid is going to be just that, where the methyl group has been removed and replaced with hydrogen. So that's benzoic acid. And methanol from the methyl group on the methyl benzoate. Questions on Fischer esterification? Yes. Yes.
Like, I have a lot of questions.
I,
Have there been a person ever like switched out someone's, I think it was the methanol for just winter people?
oh, methyl salicylate?
That would suck, but like, it'd be kind of fun.
But it's the same thing. It's not an art.
Switched out.
Oh, I don't know.
And then
That's really the only, that's like the class, that's like really the only compound that has that smell.
so I would actually say, like, you could switch out something.
Yeah. But then also that makes me think of something. If you see that something has natural versus artificial wintergreen in it, there's no difference, really. It's the same compound, just one comes from plants and the other is made in a lab. Anyway. And so oh my God, come on. Last really short method for synthesizing esters, we actually already talked about. And that's acid chlorides. So if we take an acid chloride, react it with an alcohol. So this looks like the Fischer esterification, except we're starting from an acid chloride. In this case, we don't need a catalyst. We don't need heat. In fact, react probably generate quite a bit of heat. And that's going to give us our ester. Okay, so let's talk about some reactions that esters undergo. The first one is cool. Saponification. So the SAP here is the same root word as soap, because this is sort of the classic process for making soap. So you take an ester. This could be like a triglyceride from fat or something. And we react it with sodium hydroxide and then acid after the reaction's done. Saponification is just base hydrolysis of an ester. And we get a carboxylic acid and an alcohol. Or you could say, all right, well, let's just do the sodium hydroxide. That's going to give us a carboxylate. So if R is just a giant chain of carbon atoms, like 20 or so, something like this, you do this reaction, then this sodium carboxylate is soap. So sodium salts are usually solid soaps. Potassium is generally for liquid soaps, but anyway, not really a soap making class or anything, but if you're actually trying to make the carboxylic acid, then you just treat this with some acid, and then you get the free carboxylic acid. The second method is the second reaction is acid hydrolysis. Well, we just talked about that. That's just the reverse of the Fischer esterification reaction. Third is not a very good reaction, but it's there, and that's aminolysis. take an ester and add to it ammonia or some other amine. The reaction's pretty slow, and so it's not used particularly often, but you can convert an ester to an amide by doing this reaction. And the last reaction we'll do with esters is the Grignard reaction again. But here we've got one potential issue that's kind of annoying, but can be useful. So this is going to look like all the Grignard reactions we've done before up to a point. So we take our ester and we add excess Grignard reagent. So here I'm just saying R prime and R double prime. These are all just different R groups. They don't necessarily have to be different, but they can be. So we do Grignard reagent and then aqueous workup. You might think that if we just added one equivalent of the Grignard reagent that we could get an alcohol or something like that. But it turns out that that doesn't work. Instead, you are always going to add two equivalents of the Grignard reagent. So that product ends up looking like this. It's a tertiary alcohol. And as you'll notice, R prime, which was the group originally on the oxygen atom of the ester, is completely gone from the product. We've only got R and R double prime. So adding one equivalent of Grignard reagent is, well, if you actually did that, just added one equivalent, you would only get half of the ester converted to that alcohol product. But it's always going to go all the way and add two R groups, two R double prime groups, that is, onto our tertiary alcohol. Questions on esters?
Okay, sorry.
Just what? Yeah, alkanes, they could be a benzene ring. But yeah, alkanes of sort of any different variety. So let's do an example there. I've got a little bit of time. So what if we started with of this last part, the Grignard reagent. Let's use ethyl acetate. It's a common solvent. And what sort of Grignard reagent should we add? What do I want to do? Let's do and let's just do phenyl Grignard. So if we add phenyl magnesium bromide, which is just benzene ring with magnesium bromide on it, what are we going to get? Okay, well, we're going to have a tertiary alcohol. So an alcohol with three things on it. One of those things will be the group that was on the carbonyl side of the ester. So in our generalized example, that's R. In the specific example, that's the methyl group on the left. So I'm going to write H3C. Why not do that here too? Okay, so that's our methyl group. That's going to stay on the alcohol in the product. What about that R group, the ethyl group? Where is that going to be in our product? Yep. Whee! Yes. So that is the same as R prime in the general example. And so that's going to be gone, no longer part of the molecule. It's going to be ethanol as a side product, but whatever, not important for our organic product. And we get two equivalents of whatever was attached to the magnesium bromide. So in that case, that's our benzene ring or our phenyl group. So you could either write this like that. And then also here, we need to say that that's excess phenyl magnesium bromide, or at least two equivalents. Or we could just write it like that, writing out the benzene rings like so. So if you're looking for, so like say I didn't give you that, and I said, okay, given that that's the product of the reaction, and we've seen what we've done to the starting material, we added phenyl magnesium bromide and then water. What starting material could that have come from? Now there's actually an infinite number of answers here, but you'll say, okay, well, if we add two equivalents of this Grignard reagent, which is the phenyl group, that means that we certainly could have come from an ester, because esters will always add two equivalents of Grignard to them. We know what the group on the carbonyl side of the ester is going to be, and that's the CH3, the methyl group right there. So you could go as far as saying that we have an ester with a CH3 group on the carbonyl side, but on the oxygen, on the other side, that can really be any R group that you like. So I could have said, all right, let's do a tert-butyl group instead. So this is now butyl acetate, although you wouldn't need to name it, definitely. That would be a correct answer, because if you do this Grignard reaction, you're going to get that same product at the end. Because
Not important.
it's not, yep, not important.
So in a lab, would there be a reason to use one or the other essentially twice that way?
Yeah, you just use, well, if you're doing this example, you'd use ethyl acetate because it's cheap. Hey, use 20. You want to do this reaction with methyl benzoate or with a benzoate ester? You would use methyl benzoate because that's the cheapest. Yes.
The oxygen goes from that's attached to that R prime group. It's not.
Yeah, I should have. Let's see. I'll put that.
Does that
Okay, so I know I said R prime is completely gone. Really, it's the alcohol. Completely gone. But it is not incorporated into the major organic product, which is what I'm going to ask you about. All right, we're going to do the last functional group briefly because there's not too much to talk about, and that way we'll only have a little bit left next time, and we can do some practice as well. Okay, and so amides. All right, for the synthesis of amides, there's nothing new that I want you to know that we haven't already talked about for how to make amides. I think for all of the functional groups we've talked about, I think so. There's been a way to make an amide from that other functional group. So we're kind of already done with that part. But let's talk about reactions of amides. So just as a little brief review here, we can have some different kinds of amides. The sort of the parent class is the primary amide, the first one, which has an NH2 group on it. But you can substitute those hydrogens for other functional groups, other alkyl groups. Ugh, I should probably do R prime and R double prime to say that they can be different. But any of these functional groups are amides. You're just looking for that carbonyl next to the nitrogen in order to identify the functional group. So we can do acid hydrolysis. We're also going to do base hydrolysis, but we can do acid hydrolysis of amides. So when we talked about esters, we did, well, the acid hydrolysis of esters is just the reverse of the Fischer esterification reaction. That reaction is reversible, right? We can go both directions. This reaction here for the amides is not reversible, and here's why. We are going to make a carboxylic acid. Maybe not a surprise there. But the side product is a salt, ammonium chloride. And if you're doing this in an organic solution where you have like an organic solvent and just a little bit of acid, this salt is going to precipitate out of solution and drive the reaction forward. But the main thing to know here is that This is not a reversible reaction, which is good because that's one less thing you got to remember. You don't have to remember the reverse reaction or anything like that. Go on the next page. Base hydrolysis is very similar. But it's a lot slower. And it requires pretty significant heating to get that to happen. Now, because you're under basic conditions and you have hydroxide around, you can't make the acid because that's just going to react with your base that you included. And so the product of this is actually going to be carboxylate, should be sodium, salt, and like the acid hydrolysis up here, that reaction is not reversible. Really, the only other thing you can do with amides is reduce them. And this is actually kind of useful. Last thing, I promise. This is kind of useful because well, we've talked about a lot of reactions that convert things into amides. And so what you can do from this point, once you've got your amide, treat it with lithium aluminum hydride. Nope. Nope. Thank you. And we get an amine, which is a very useful functional group in itself. So we have here complete removal of oxygen from the organic molecule. So let's say that we have this molecule, which is an amide, right? It's got the carbonyl next to the nitrogen, but we have two other R groups, a methyl and an ethyl group on the amide, and that's okay. They're just going to chill, and all the interesting stuff is going to happen to the carbonyl. So we keep the benzene ring, we keep the nitrogen, and we also keep all the substituents on the nitrogen. We just get rid of the carbonyl, and we have hydrogens there. So if you really want, you can just not even draw those hydrogens. All right, that's amides. Next time we'll talk about nitriles and do some review, and then we'll go on to chapter 21. Okay. Hang on, sorry, let me